Hello everyone, my name is Fatimatu Zora and I'm from Texas State University. My research topic is smart automation of an integrated water system. In this presentation, I will explain what are the problems and potential solutions that my research work is focused on, some literature highlights, methods and materials I implemented, results, and finally conclusion and future work. As a mechanical and manufacturing engineer, my work focuses on automated systems and control, which, according to SME, belongs to one of the four pillars of manufacturing knowledge. Scarcity of fresh water is a global problem. In 1995, the world population was 5.7 billion, and the orange color on this graph shows more than 40% water withdrawal regions. The prediction for 2025 with a population of 8.2 billion shows the extension of these areas. The overall water withdrawal has been increased around the world. Currently, 1.2 billion people do not have access to safe water. 40% world population faces water scarcity per year. The table on the right shows the inventory of water at Earth's surface, and a very tiny amount of total water is accessible to us for use. Our focus of solving the water scarcity problem is to go off-grid. That means not connected to any supply water network system, especially for the remote areas where people do not have access to safe water and the place is too far from the developed areas to establish a water supply line. So our first potential solution is atmospheric water generator, or in short AWG. This is an off-grid source of water and free in terms that the water generated by this device comes from the surrounding moisture in the air. And this moisture comes from the biosphere due to evaporation in water cycle. But this generation process can be energy intensive and inconsistent in nature due to variation in temperature and relative humidity in the atmosphere, as the amount of water production largely depends on these factors. The graph on the right shows this device can produce up to 30 liters of water while operated in the most favorable atmospheric condition. And for the most favorable condition is for temperature is above 60 degrees Fahrenheit and relative humidity is above 40%. This is the picture of AquaBoy Pro atmospheric water generator that we used for this work. The second potential solution is rain harvesting system, or in short RHS. This is also independent of supply water network, which makes it off-grid water. Free of cost in that sense that it is a natural phenomenon, but unpredictable as well, and the amount of rainfall is never constant. The system is pretty straightforward. The rain falls on the catchment area and collected in a reservoir, filtered, and then supplied to the user. Figure 5 shows the rainwater harvesting system at Freeman Center, San Marcos, Texas, which is our project site. Now, apart from having a water shortage, we also have a significant problem regarding the way the water is consumed. Worldwide, about 70% fresh water on average is used for agriculture. According to the World Bank Group data, there is an expectation of 50% increase in cultivated production and 15% increase in freshwater withdrawals for the increased population by 2050. A potential solution can be vertical farming, because this farming is developed in a controlled environment and does not require land. It can be established anywhere, even in the remote areas. Hence, this can be called off-grid farming. It uses only 20% water compared to traditional farming because the water doesn't get lost by soil absorption. This is actually hydroponic farming, which is placed vertically to utilize vertical space. Hydroponic system is growing plants in nutrient solutions as shown in this figure. Some other benefits of this system are double growth rate, nutrition efficiency, fewer pesticides, etc. This is a good example of continuous water demand, and that's why I decided to use the Evergreen project of vertical farming system to be the application site for the smart integrated water system and designed it accordingly. My research focus is to introduce smart automation to the integrated system, which combines rain harvesting system and smart AWG as a backup. It is done by auto-regulating the water generation for AWG and by automatic refill in nutrition supply tank in the delivery side. The table on the right shows my novelty of work where I integrated these two systems and implemented automatic control over this. My methods and materials follows these 6 steps. First, some data analysis and concept integration, then drawing the 3D CAD model for better visualization, selecting electrical and mechanical components that will be used for the automation, logic development for Arduino controller, fabrication or connection, and finally experimentation and validation. I'll explain these steps on my following slides. So the data analysis was performed based on this 4 years period of data which is collected in San Marcos, Texas for historical rainfall and the water generation from AWG. The graph in figure 10 shows that the integrated system of rain and smart AWG actually provides more consistency over water supply than rainfall only. The AWG is considered a smart AWG when it is turned on based on the following conditions. There is a water demand, the rainfall is below historical average, and ambient condition is feasible to run the atmospheric water generator. So the AWG in this integrated system will work only as a backup system for rain harvesting system. And the reason for that rain is bigger in amount and AWG usually compared to that is very small amount of water production. This can be designed based on the demand and operational feasibility, which is again temperature and relative humidity. The calculation of coefficient of variation for this integrated system, that is 0.44 being less than 1, also gives us the same conclusion about the consistency. Both the rain harvesting system and AWG system have some similar subsystems such as the reservoir, filters, supply line, pump, etc. Instead of having them on each separate system, we combine them as one. This schematic shows the idea of integration with the real pictures from our Fremont Center site. The whole system can be categorized into two sides, generation or collection and delivery or supply side. This is the 3D CAD model that was drawn for a better visualization of the system. This is the smart integrated system. You can see the complete fabrication or installation. This is the evergreen site. Rain falls on the roof and is stored in the main tank. AWG generated water is stored in the secondary tank and then pumped to the main reservoir. Water is purified through a set of filters so that it can also be used for potable use. Finally, it is delivered to the supply tanks for nutrition solution to the vertical farming. Figure 12 shows the logic flow of the automation of this collection site, and figure 13 shows all the connections lines for power, logic, and water flow where this logic was applied. This whole system gets power if the water level is below 1000 gallon in the primary reservoir by this 110-volt AC source. The logic then starts assessing the temperature and relative humidity range, which is 30 for humidity 30 to 100%, for temperature is 55 to 120 degrees Fahrenheit. So depending on the feedback, it decides on whether to turn on the AWG or to keep it off. Then it takes feedback from the float, which is here for the secondary reservoir. And if this tank is full from the water that is generated by the AWG, then the Arduino turns on this. There's a small pump for 20 minutes to transfer this water into the primary reservoir. Similar figures are shown here for the delivery side. There are 8 supply tanks, so 8 floats and 8 solenoid valves. There are 2 Arduinos, each controls a set of 4 float, 4 solenoid. For better visualization, only one set of each component is shown in this figure, and each float have this logic shown in figure 16. If this float signals the low level of water, the Arduino switches on the respective solenoid to keep it open for 5 minutes for automatic refill of the tank to desired level. The water comes from the primary reservoir and filtered on the way to this part. The solenoid stays open for 5 minutes. Now, due to COVID-19 pandemic situation, it was not possible to completely install this full automation on site. There are some work required related to infrastructure development and physical labor, such as lifting the AWG on their higher positions, water line installation from the distributor to the supply tank, etc. However, this electrical system is completely tested in experimental setup and partially on site. On the first video, one Arduino controlling 4 floats and 4 relay switches, and these relay switches turns on and off the solenoids. The floats are numbered according to the pin numbers they are connected on the Arduino board. For making a short video, instead of letting the solenoid run for 5 minutes, I did it for 5 seconds here. In this video, you see no matter if one or multiple floats are sending a low water level signal, the logic is working to open the respective solenoids. On the second video, this whole setup from first video was taken on site and float 7 was installed in one of the supply tanks. A respective solenoid with water line connection was also established. As you see, this is the distributor line, and a flexible water pipeline was connected to the solenoid valve. Here it is, and the electrical connection was developed. Right now, this is the float 7 sending this signal of a low water level. So the switches are on. All other 3 floats are also sending the signal of low water level. So there are 4 switches on, and the water is flowing in to refill the tank. Well, to make the video short, I manually pull up the float switch to send us high level water signal, and this respective solenoid closes and the water stops coming in. As a conclusion, I can say that the areas with a year-round extreme weather might not be suitable for this kind of integrated water system. And we don't have control over collection of rain or generation of AWG water, but we can definitely control over the operation of the system, which is introducing smart automation. This smart automation saves energy and labor because otherwise someone has to stay on site to, to do all this operation. And this also eliminates the necessity of extra electrical equipments like the pump in AWG to run. So it actually saves energy and in terms of money. Potential water source for rural areas with water scarcity at comparatively lower cost. This has the flexibility to scale or adjust components based on the local area, rainfall, and atmospheric condition and type of application. This is a study that shows the fraction of favorable time for AWG based on meteorological data from 2005 to 2014, combined with water scarcity map. So again, if you see for the Texas area, it's again the favorable time is greater than 50%, which is considered as a water scarce region. And for most of the regions also the favorable time is really good. So this is actually can be a feasible application. Some potential future work might include sophisticated data collection method regarding water uses, a systematic economic analysis for water cost, investment, considering the depreciation and break-even point, investigation of an integrated rain harvesting system, AWG, and supply water system. Application of upgraded technologies to offer more flexible decision in automation, for example, wireless technologies, cloud data collection, rain forecasting database decision might make this system more efficient. So these are the references that I used for this presentation. And thank you very much everyone for watching this presentation. I really appreciate your time and patience. If you are interested to know more about my research, please contact me at my email or on my website. Thank you.